Our whole modern world is basically a giant, intricate machine. From the power plants keeping our lights on to the factories building, well, everything, we count on these complex systems to just work. But every single one of them has a secret, a story that it's telling all the time, if we just knew how to listen.
Seriously, just think about it for a second. Almost every single product you touch, every service you use, it's all made possible by some kind of industrial machinery humming away somewhere behind the scenes. It's this massive, invisible network that we totally take for granted. And here's the thing, the super reliable world we've built, it's actually a lot more fragile than you'd think. Because all machines, it doesn't matter how well built they all eventually wear down. And when a machine suddenly stops, it's not just some small inconvenience. A surprise failure can shut down a whole production line, cost a company millions, and cause this huge ripple effect of problems. So the big question is, can we actually see it coming?
Okay, so let's treat this like a crime scene. A machine has failed. Our job isn't just to figure out why it happened. The real mission is to figure out how to stop it from ever happening again. So this graph right here is really fascinating. It's called the bathtub curve, and it basically tells the life story of almost any machine you can think of. See, at the very beginning, there's a pretty high chance of failure. That's when you're just working out the bugs, Then you hit this long sweet spot of reliable, normal operation. But it's inevitable. As parts get older and start to wear out, that failure rate starts to creep up again. That's the danger zone, and that's exactly what we need to learn how to predict.
So if we know failure is coming eventually, how do we get out ahead of it?
Well, for a long, long time, the answer wasn't all that clever. It basically came down to a choice between two old-school approaches.
So on one side, you've got what's called corrective maintenance. That's basically the run-it-till-it-breaks method. Just cross your fingers and hope for the best. It's simple, sure, but it's also chaotic and incredibly expensive when things finally go pop. On the other side, you have traditional preventive maintenance. This is where you fix things on a strict schedule, like replacing a part every 1,000 hours, no matter what. It's definitely better, but you end up wasting a ton of time and money replacing parts that were still perfectly good.
But what if there was a third way, a much, much smarter way? What if, instead of just guessing, we could actually ask the machine how it's doing? That's the whole idea behind condition monitoring. We listen for the earliest signs of trouble, and we only act when we need to. But, and this is the crucial part, we act before it breaks.
And this chart here just lays it all out perfectly. Way over on the right, you've got that reactive, run-to-failure approach. And on the left, you see the old-school scheduled maintenance. But look right there in the middle. Condition-based maintenance, or CBM. This is our detective's go-to method. Its whole objective isn't based on a calendar or a breakdown. It's based on a measured condition compared to a defined standard. In other words, it's all about evidence, real-time evidence, coming straight from the machine itself.
So how does a machine actually talk to us? What is this secret language we need to learn? Well, the number one clue, the one that tells us almost everything we need to know, is vibration. At the end of the day, vibration is really just movement. Every single rotating machine, whether it's a motor, a pump, you name it, vibrates. A healthy machine has this consistent, predictable pattern of vibration. It's kind of like its unique heartbeat. But the moment something starts to go wrong, that signature, that heartbeat, changes. And that is the machine's way of telling us that it's in trouble. And these are the usual suspects that cause all that trouble. Each one of these problems, from something simple like an imbalance to a worn-out gear, creates a very specific and, more importantly, a very identifiable change in the machine's vibration. So our job as the detectives is to figure out which suspect is causing the problem by analyzing its unique vibration fingerprint.
Okay, so we've got our suspects lined up. Now it's time to head to the forensics lab and see how we actually analyze the evidence. How do we take these tiny little movements and turn them into information we can actually use? Well, it's a very systematic process. The whole investigation follows 5 pretty clear steps. First, you have to sense the vibration. Then you condition the signal, which is just a fancy way of saying you clean up any background noise. You record the data, and then you get to the most important part. You display and analyze it. And finally, you use that analysis to diagnose the problem and figure out how to fix it.
This little guy right here is the heart of the whole operation. It's an accelerometer, which is basically our microphone for listening to the machine. And inside is this special material called a piezoelectric crystal. And it has this really cool property. When you squeeze it, it generates a tiny bit of electricity. So as the machine vibrates, it's constantly squeezing that crystal, creating an electrical signal that is a perfect recording of every single shudder and shake. Now, this raw signal on the left, yeah, it looks like a jumbled mess, right? How in the world do you make sense of that? Well, this is the magic trick. Using a mathematical tool called the fast Fourier transform, or FFT, we can do something pretty incredible. It acts just like a prism for light, but for sound. It takes that messy, jumbled signal and breaks it down into all of its individual frequencies. The result, over on the right, is this beautiful, clean spectrum. Each one of those peaks on the graph is a clue, pointing directly to one of our suspects. Okay, theory is all well and good, but let's see our detective in action. Let's take a look at a real-world case, a simple industrial fan. Our mission? Can we spot the telltale fingerprint of a super common problem? Unbalance. Here it is. This is the evidence. Take a look at the graph on the left. This is the vibration signature of our healthy, perfectly balanced fan. You can see a couple of small peaks, but pay attention to that one right around 23 Hertz. That's the fan's normal running speed. Okay, now look at the graph on the right. For this one, we deliberately added a tiny weight to one of the fan blades to create an imbalance. And the change, well, it's impossible to miss. That same peak at 23 Hertz has absolutely exploded. Just how big was that explosion? The vibration at that one specific frequency shot up by a staggering 400%. That's not just a clue, my friends. That is a smoking gun. It is a crystal clear, quantifiable signal that a very specific problem, unbalance, is happening. And just like that, the case is cracked. By listening to the machine's vibrations and decoding its language, we didn't just find a problem, we pinpointed the exact nature of the problem. And that lets us make a precise, efficient repair long before a catastrophic failure could ever happen. So, okay, this is some really cool detective work. But why does it all matter in the real world? Well, the payoff for learning to listen to our machines it's absolutely immense. I mean, just look at these numbers. They're staggering. We're talking about a 50 to 80% reduction in maintenance and repair costs, a 30% or more reduction in what they have to spend on spare parts. And what does all that saved time and money lead to? A massive increase in overall profitability. This isn't just about fixing machines anymore. It's about completely changing the economics of how industry works. And that really brings us to a final thought. We've figured out how to decode this secret language of machines. It kind of makes you wonder, doesn't it? What other systems, both natural and man-made, are out there right now, constantly sending out signals? What other crucial stories are unfolding all around us, just waiting for the right person to come along and listen?